Hello students, it's Dr. Church, and today we're going to begin a new chapter on ecology and populations. And this is an interesting section, Chapter 6, Population and Community Ecology, mainly because the study of populations is a big deal when we talk about how the abundance or lack of species within an ecology can affect how that ecology functions. Now, of course, this could be something as small as a knot in a tree with um, organisms within it, or as large as the entire global world population. And so the study of populations is a pretty important topic for us to take a look at. So let's go ahead and switch over and take a look at Module 18, the abundance and distribution of populations. Now, for this module, we've got three learning objectives. Explain how nature exists at several levels of complexity. Let's take a look at that. Discussing the characteristics of populations and contrasting the effects of density-dependent and density-independent factors on population. And we'll see that density is population density. Now, here's a question. Why might it be important to understand the distribution patterns of populations? Let's think about that for a second. Why might it be important to understand the distribution patterns of populations? Well, if we can understand the factors that influence the distribution of populations, we might be able to better equip ourselves to protect and preserve populations. We're going to learn that sometimes populations can be too small and run the risk of extinction. Sometimes populations can be too large and utilize all the resources in a particular ecology. And so either one of those extremes can lead to bad outcomes for that particular population. So if we can understand those populations, and again, we are scientists, right? We're applying the science to ecology and our study of the environment. And so as we understand the patterns and distributions, we might be able to control invasive species that disrupt biodiversity, and there are other ways that we can manage and make good decisions about how populations can function within an ecology. Now, if we take a look at it, we've talked about the biosphere, right? We've talked about the different spheres. We have a general flow of ecosystems and how energy flows into and out of an ecosystem, how matter flows into and out of an ecosystem. We've talked just a little bit about communities, but here we're kind of moving down. We've kind of moved down this nature of complexity, and now we're looking at population dynamics, and then down within the population, and we've actually already talked a little bit about individual survival. So these are our different levels of complexity as they move up from the individual to populations to communities to ecosystems and to the different biospheres, and so are the different spheres. And so some of these we've already began to discuss in our class. Well, let's put some terms in place. The first is going to be, what is a population? The individuals that belong to the same species and live in a given area at a particular time. So that's going to be a population. Okay, just basic definition. What's a community? Remember, we're going up those levels of complexity here. Well, these are all the populations of organisms within a given area. So we might have a population of rabbits within a given area, and then we might have a population of foxes within a given area, and then the community would be comprised of both rabbits and foxes, and then the many, probably hundreds or even thousands of other organisms that comprise the populations within that area. Population ecology then studies the factors that cause these populations to change, to either increase or decrease. And so that's what we're going to study. Populations have distinctive characteristics. There are five basic characteristics of a population. So one is the population size, and often you'll see the variable that's attached to population size is a capital N. Then we have the population density, the population distribution, what's called the sex ratio, that's male to female, and then the age structure, how old are the individuals within that population, and the distribution. I thought this was just a little bit of interesting demographic here showing the distribution of the world population. Of course, you can see the two major populations of the world being China and India. Then you've got the US, Indonesia, Brazil, Pakistan, Nigeria, Bangladesh, and Russia, then Mexico, and on down to some of the smaller nations in terms of that. But you can see how large of an impact that we have from just India and China, okay, on population. So that's why they are very important sometimes in our study of population dynamics. Well, let's take a look at these five characteristics individually. The first is population size. We're just counting numbers. Now, this is going to be the total number of individuals in a defined area at a given time. When we look at that, we'll often see that we have populations that can be distributed over time, and normally there's going to be what's called an optimum population, where within a given ecosystem for a particular period of time, if there are too few, then that runs the risk of being underpopulated. And if there are too many, that runs the risk of being overpopulated. And so getting that population size is an important statistic for us to calculate and to understand. We're actually in the middle of the 2020 census right now. And so you've probably heard a lot of advertisements on online or on the news and just TV. You may even have had somebody come and take your information. And what the United States is doing is actually counting population sizes and distributions. And then that data is actually used for distributions of aid and governmental support and lots of other things, healthcare. Those are very important numbers to calculate. So again, just looking at population size. Well, what's the second characteristic? Well, it's population density. If you look, this is just a population density in the United States. You can see these dots represent like the population counts, and so you'll see these areas along the East Coast, and we know that these are very densely populated areas. Up here in Chicago and Michigan, these very densely populated areas. Of course, Southern California, around the Los Angeles area, then on up towards San Francisco and Washington. But now if you go out west, here's Wyoming in here. That's not very densely populated. So if you want to go out and be in a very much less densely populated area than we have here in North Carolina, then head out to Wyoming, Colorado, Idaho, Nevada, Oregon, places like that, and you can see. But if you have a population density, really is getting at that number of within a given area. So that's going to be population, right, per unit area. So that might be a square mile, right, or something like that. So we'll actually do some mathematical calculations with these numbers. Well, here's population distribution. Here's our third characteristic, a description of how individuals are distributed with respect to one another. And so population density is those straight numbers per unit area. This is going to be how the population is distributed with respect to one another. And so again, you'll see some commonalities there with the more densely populated areas versus the less. But if we look at, we can see here the main thing off this graph is if we look at China and India, right, we see the distribution of populations being in really a relatively small area there. And so, you know, this can be interesting data for scientists to use. And of course, here's Western Europe, here's Spain. Of course, England is off the coast of Europe, but you can see how populations are distributed. Well, the fourth thing is characteristic is going to be the ratio of male, right, to female. Now, this is an interesting. You may learn something here, but this is the ratio of males to females within a population. This is an interesting graphic we pulled, and what this shows is this is the number of males per 100 females. So it's a comparative statistic. If you look at the world population, there's not a huge difference between the number of females and the number of males. Now, in our species, generally speaking, if we allow nature to run its course, what you'll have is essentially a 50-50 distribution of males to females, right? You'll have roughly the same number of male births as you will female births. But you'll notice that that's not necessarily how things are distributed. If you look at this graphic now in the United States, that's roughly true. Okay, so you have 99.4 males to every 100, so you roughly 99 to 100. So that's a pretty even distribution. But if you look at, let's say, Brazil, you've got many more females than you have males. That's a 90 to 97 ratio. So you have 7 more females for each male. So you'll see that in this area. And so the pink shaded areas are predominantly, you know, more female, but then the blue shaded areas and the darker blue it is, the more males you have. And so in this case, we have it's 102 to 180, right? So 102 males, so there's 102 to 100 females in these areas. So what's actually happened is that I think that there have been some policies that have been put in place that have favored male births. I know China had put in policies, and in India, unfortunately, males are considered as you know, I don't agree with this, but you know, more valuable in some social sense, and so they've skewed births and to the male side, and that's what you see there. The life expectancy of females is generally longer, and so if nature runs its course, you might have just a slightly more female dominated population, but I think there have been policies that have affected that in some of these Asian countries, you know, versus some of the more Western countries. But that's, you know, looking at the male to female ratios is another important statistic characteristic of populations. And then finally, it's just age structure. This is what are the age distributions, and obviously as you would go up to, you know, people who are in their 90s and in their 80s and their 70s, the population should be distributed this way, is as you've got more, and again on this side this is going to be males in blue and females and the kind of red pink areas, and then these, as you go up the age distribution chart, that's age from 0 to 100, and you'll have people that in populations, the distribution of young from 0 to 4 is going to be your greatest, and then obviously as people age, then the death rate begins to decrease the number of people within a particular population. Now, as when we study population distributions and age structure distributions in the future, we're going to look at particular countries that had birth control policies in place for several decades, that came out of really movements of the 50s and 60s. And this chart won't look like this. You'll see distributions where the aged population is as significant as the middle adult, young adult, and child populations. And so those societies are going to have real issues with that, and we'll talk more about that later. But the distribution of age is very important. Now, a couple other ideas, and then we'll wrap this section up. Population is affected by what's called density dependent and density independent factors. So density dependent, and this is the density of the population. So density dependent factors are those factors that influence population size based on the number of individuals that are in that population. Now, this is very easy to see when you think about a density dependent factor like predation, for example. There are always limiting resources, and the higher the population goes, the more resources you need within that ecology to support the increased numbers of individuals. And so there are density dependent factors, like these are limiting resources generally that individuals within the population cannot live without. And so these things would be those sources that provide resources to the individuals that are in that population. And as the numbers go up, the limits begin to kick in. Now, there are density independent factors, right? These are factors that control population size that really do not depend on the number of individuals within that ecology, but they're density independent factors. And these are things like droughts, and these are factors that really have the same effect on the probability of survival, but the amount of reproduction at any population size is not dependent on the number, but things like hurricanes and droughts and tornadoes and storms that come through can decimate populations, and it doesn't really matter how many are there. So let's just take a look at a couple of these limiting factors. And if we look at the population size, here's your in the red circle are density dependent, and in this red circle are density independent. So competition, predation, disease, that's density dependent, because as populations go up, competition goes up, predation is affected, disease within a population generally goes up with higher numbers. But things that are density independent are like natural disasters, forest fires, hurricanes, tornadoes, droughts, things of that nature that can limit population size, but don't depend on the number that are already in that population. Now, there's one more important concept for us to learn, and that's the notion of carrying capacity. And what is this? It's the limit to the number of individuals that can exist in a population. And there was a study that was done by a scientist, Professor Gauss, and he put bacteria into a test tube and essentially controlled the amount of food that was available, and he noticed that there was always what was called a limiting capacity, right? The more food that was available, then the bacteria could go ahead and continue to thrive because the resources were available, but eventually it would get to a limit, right? And so in a low food supply, the carrying capacity of that environment, let's say, got to 100. If we increase the food supply, the carrying capacity might get to, say, 200, right? So the ecology could support a higher number of individuals, but regardless, there was always a limiting factor, a limiting resource that would determine what was called the carrying capacity. In other words, like putting rocks in a basket. There's only so many that you can put in the basket and carry them until it overflows, and it just can't carry anymore. Now, the variable that's assigned to that is this capital K. Okay, kind of confusing. It's not a C, but it's a capital K for carrying capacity, and it would be the number of individuals, are again the population size up to the limits. Okay, now there are 3 assignments that I have for you. The first is the case study from the New England forest, as I think it's a very interesting case study where the forests were actually cut down and grew back, and that's an interesting study. The Great Texas Mosquito Mystery, that's from Activity 6.2, and again, that's an interesting, and then one that's maybe not so much fun, but of course I love math, but some of you may not. But yeah, practicing your math skills in terms of looking at exponential growth and graphing and a couple other things that's really important for you to be able to do. Okay, so this is our introduction to module 18 and populations. And it's really an interesting study, and it's very important for us to understand populations, especially as we talk about the growth in the human population and how it affects environmental science long term. All right, well, I hope you learned something today. Let's keep learning.